Hello, good day everybody. My name is Science Waiter Rashida Estrada and I am from BSAF 2-3. When you are a student pilot like me or a cadet pilot, when you're first learning to fly, there's undoubtedly a lot of information to conquer. In order to make learning a lot easier, complex aerodynamic concepts are often simplified, and while that's not a bad thing, there are some common misconceptions out there. It's okay since we are all students, we are all trying to learn. So I'm just trying to help you understand some of the things. Uh, yeah, misconceptions. So here are 4 common misconceptions and what really happens in each scenario. Ground effect is a cushion of air. If you spend any time flying, you're probably familiar with ground effect. It's a thing that makes you float way past your touchdown point on landing. You've also probably heard that ground effect is a cushion of air and that your wings compress the air beneath them as you get close to the runway. Here's the real story. As you fly through the air, your wings create wingtip vortices as you get closer to the ground within a wingspan or less. Your wingtip vortices are much smaller because the ground limits the size of your vortices. This also means your wings create less downwash. With less downwash, your induced drag is reduced. Okay, I know you're bored, so here is to simulate your brain. Your lift vector will always be perpendicular to the relative wind. Why does that matter? Because with less downwash, your lift vector isn't pointed rearward as much. This means you will have more vertical lift, which will oppose your aircraft's weight, and less lift pointing backwards, which creates induced drag. So I know your brain's a bit smudged up with all the information, so here. Bernoulli's principle is the complete answer to how lift is generated, regardless if you are a 1,000-hour airline pilot or a newly minted student pilot like me. You probably heard that lift is created through Bernoulli's principle by creating an area of low pressure on the top part of the wing and a region of high pressure on the bottom. This is true partially, however, to fully explain it, your plane's lift is not created by just one method. It's a combination of several. Even NASA acknowledges that the debate over how lift is generated is not definitely settled. But you should know that it is a combination of Bernoulli's principle, Newtonian deflection, and the Coanda effect. The two main schools of thought are Bernoulli and Newton. Bernoulli's explanation for lift is that an area of low pressure is created on the top of the wing because the air moves over the top at a higher velocity on the bottom of the wing. On the bottom of the wing, a region of higher pressure is created as a result of the lower velocity of the air moving on the underside of the wing. The difference in pressure is what creates lift according to this theory. The theory called Newtonian deflection or skipping stone can be easily modeled by putting your hand out the window of your car while it's moving. As you increase the angle of attack, you get more lift until suddenly your hand stalls. This phenomenon is a product of Newton's third law, the one about equal and opposite reactions. Lastly, there is the Coanda effect. Coanda effect is the tendency of a fluid like air to stay attached to a curved surface like your wing. Coanda effect deflects incoming air that's coming over to the top of the wing down to the back of the airfoil, providing lift. And the interesting thing about lift theories is that currently there is not an individual theory that matches the measurements taken by scientists in the field. Even when combining them, there is still an unknown. Unknown? Huh? So for our third, I know I'm losing you a bit. So here's a bit of brain simulation to keep you interested. Maximum demonstrated crosswind component is a limitation. You should always have a healthy respect for aircraft's published maximum demonstrated crosswind component. That being said, unless your POH specifies it, the maximum demonstrated crosswind component is not a limitation. as a Part 91 pilot, it's from the website. It's up to you, the pilot and command, to determine how much crosswind you are comfortable handling.
Yes.
However, for insurance and safety reasons, many aircraft fleets, flight schools, and commercial operators have crosswind limitations that their pilot must comply with. Always think twice before you choose to land in conditions beyond your plane's maximum demonstrated crosswind component. So for our fourth myth, I will be having my girlfriend to read the script, but I'm scared that Sir, he might give her my grades for this video. So here.
Do I just read it?
Of course. Stop telling everybody that I'm reading something. I'm not reading something.
The most likely place to stall in the...
Okay, that's too slow for everybody. The most likely place to stall in the pattern is base to final. You should always be aware of your airspeed and stall characteristics in the pattern. After all, you are close to the ground, so stall recovery can be difficult or impossible. According to the AOPA Flight Safety Institute, 51% of all unintentional stalls occur in pattern, while downwind to base and base to final turn stalls are the most likely to be fatal, which is about 66% and 80% respectively. They are not the most likely place to stall in the pattern. According to AOPA's data, 89.3% of traffic pattern stalls occur on, over, or beyond the runway. What are the scenarios where these stalls might happen? Takeoff and go around, or are two of the most common when you're low and relatively slow. So I think that would be it for our video. Sir, if you are not satisfied with the video, I would happily make another one with a formal approach if you would like that. Okay, thank you, sir, and for everyone that's watching. Thank you.